Question 3 is one of those off-the-wall questions that you have to be ready for, which is about a reaction that you have never seen before and that there's absolutely no reason you should know anything about. But they will sometimes put these things into exams just to see how good you are at applying the sort of principles that you've learnt when you're not applying them to reactions that you actually know about. So the first question, for example, looking at this reaction, just said, what kind of reaction is it? Now what it actually is something called a Diels-Alder 4+2 cycloaddition reaction. But obviously you're not expected to know that. What you're expected to do is simply look at that and say, right, what's happening is this reacts with this, and they just join together. They don't produce any other product, so it's an addition reaction. And that was the point, really, that it was just getting you to apply ideas you know to something that looks very unfamiliar, and you just think, right, a reaction in which two things join together, just like bromine adding to an alkene, this adding to this just produces one product, so it's an addition reaction. And of course addition reactions have an atom economy of 100% because the MR of the useful product divided by the sum of the MR of all the products is obviously just 1, because that is all the products, and therefore 1 times 100 is 100% atom economy. B then asks what you mean by a curly arrow when you're writing down a reaction mechanism. That actually is a very popular exam question, and lots of people always lose marks because they say, oh, it shows electrons moving, but it's more specific than that. A curly arrow means a pair of electrons. Okay, so it's much more specific than just saying it's some kind of electron movement. It's a pair of electrons moving. And you've got to know that, and you've got to be ready to think about that as what's going on when you're writing out mechanisms and thinking about what they mean. So then, in part C, it asks you to propose a mechanism for this reaction just using curly arrows. Now, this was a pretty ambitious question. It's something which, you know, if it came up in an exam, they would not be expecting many people to get right. But I think it's good for you to have a think about it, because it really gets you to think about what this means. So what you need to do is to compare this and this and realise that every bond that's broken, so you can see the pi bond there has gone in this product. Okay, so there's a bond broken, and here's another one that's broken, and here's another one. So all three of those pi bonds have gone in the product, and that means they're going to be at that end of a curly arrow, because the pair of electrons that was this bond has gone somewhere else. So it's going to go from where it is now to somewhere else. Well, where's it gone? Well, you can see that this carbon, which has a share of that pi bond, is, although it's lost that bond, it's now got a new bond here. So if you think about it, what's happened is that that pair of electrons that was this pi bond here has now become this sigma bond there, because remember, that's all the bond is, a pair of electrons. So this pair of electrons was a pi bond here, and it's been used to create this new bond there, because it's just that carbon using the electron pair in a different way. So how do you show that using a curly arrow? Well, remember, it starts with the bond that's being broken, and it points to the atom that the new bond is being formed to. So you draw an arrow like that. Okay, and if you think about it, that's just the same as if you have the alkene mechanism. You know, if it's adding HBr, remember, you draw the curly arrow from this bond to the hydrogen and from this bond to the bromine. And what that means is that the pair of electrons that was the pi bond is now moving out of the pi bond and is being grabbed to form a new bond to that hydrogen. So in the same way here, the pair of electrons that was that pi bond is moving out of the pi bond and is being used to form a new bond, this one, to that carbon. Now the thing that's really cool about this mechanism is that it follows that same pattern all the way around. Because of course this carbon can't accept an incoming bond unless one of its existing ones breaks. So what's going to break? Well, the pi bond breaks. Where does that pair of electrons go? Well, you can see there's another new bond here. So what's happened is that pair of electrons has come out of the pi bond and it's been used to form a new bond to that carbon. And then one more time, this carbon can't accept the incoming pair unless it lets go of one of its existing pairs. So again, its pi bond breaks. And where does it go? Well, you can see in the product, it goes here. Okay, there wasn't a pi bond there before, but now there is. And that's because this one is going to form a new bond there. And the atom that's being attacked is this one, because this one's already got a hold of that pair of electrons. So this one's going up to there. And that is your mechanism. So it's a beautiful flow of electrons like that around this, what becomes the six-membered ring. So as I say, that was an extraordinarily challenging question. It was there mainly to make you hopefully think, yeah, it's worth really thinking about what curly arrows mean. Because once you get confident with them, it's quite easy to learn to push them around like that. And once you can do that, they cease to become mystifying. They're just interesting because they give you this handle on what mechanisms are likely to be. Part D is there really so that you can test yourself on whether you have remembered what to do with enthalpy cycles, because it was actually quite a straightforward enthalpy cycle question, but obviously, you know, that's still a fairly new game to you, so it maybe it hasn't sunk in yet, and this would have told you that. If that was the message, then you know you've got to go back and really learn to do it. So the key thing is, remember with enthalpy cycle questions, first of all, you've got to draw out the cycle. Do not attempt to think, oh, I'll just crunch the numbers, I don't need to draw a cycle. You're much more likely to get it wrong if you do that, and you're much less likely to get any marks for working if you mess it up and you haven't drawn a cycle. So stick to the script, draw the cycle, and remember what you look for is what kind of data, what kind of numbers are you feeding in to the calculation. And in this case it tells you that the numbers you have are enthalpy changes of formation. As soon as you see that, you remember that what connects this side with this side in your cycle are the elements that these compounds are made from. Okay, because the enthalpy change of formation is the enthalpy change when 1 mole of a substance is formed from the elements it's made up from. So we're going to have a cycle that's based on this, which is the formation of these 2 molecules of butadiene from the elements, and this, which is the formation of the addition product from the elements, and then this, which is the overall reaction. So we can put those numbers on because it tells us that the enthalpy change of reaction is -142. Remember, with reversible reactions it's always -142 going in the forward direction, or rather the number you're given refers to the forward direction. So that's -142. So it would be +142 going that way. The delta H of formation of this compound, it tells us, is +80 kilojoules per mole. So if you make 1 mole of that compound from its constituent elements, it's +80 kilojoules per mole. So what we're asked to find is the enthalpy change of formation of buta-1,3-diene. So what we'll do is to say let X equal the delta H of formation of buta-1,3-diene, which is that. Okay, and you should write that down, and you should write it down Firstly, because that's good practice. You shouldn't just introduce X without explaining what it is. But secondly, if you had written it down, lots of you wouldn't have slipped up by forgetting that there was a factor of 2 there, which loads of you missed out in this calculation. Because here you're forming not just 1 mole of butadiene, but 2 moles of butadiene from its elements. So this is not just X, it's 2X. Okay, going that way, because you're making 2 moles of buta-1,3-diene from its elements, so it's 2 lots of the delta H of formation of 1 mole of it. Okay, so those are the data you've got to play with. So what you do then is to remember that what Hess's law says is that doing that directly, minus 142, you get the same number if you do it in 2 steps, coming down here and then up there. The sum of those 2 steps will equal that. So what are those 2 steps? Well, this one is exactly the opposite of that, because instead of going from the elements to form 2 moles of butadiene, you're going from 2 moles of butadiene back to the elements. So this is minus 2x. This one is exactly the same as that. You're just making a mole of the addition product from the elements, going the same direction as the data, so the number is the same. So that's plus 80. Once you've got that written on your diagram like that, you shouldn't get the signs messed up. But lots of people did get the signs messed up, and often it was because they hadn't done the diagram. So do that, make sure that you get these things done accurately. So now we can make our statement. Hess's law says that the overall change, minus 142, is the sum of that plus that. So minus 142 is equal to minus 2x plus 80. You've got to be incredibly careful with the signs. If you got this wrong, somewhere or other, it's usually because you got the signs wrong, or the factor of 2 there. So now we've got to rearrange that. So if we move the 2x over to that side, we get 2x minus 142 is equal to 80. And then if we move the 142 over to this side, we get 2x is equal to 222. So x is equal to 111. Okay, so that means that the answer, delta H of formation of buta-1,3-diene, is equal to plus 111. Remember, enthalpy changes must always have an explicit sign. So it's not just 111, it's plus 111 to distinguish it from minus 111. So plus 111, and it needs a unit. Kilojoules per mole is the answer. So that was actually a pretty straightforward enthalpy cycle question. If you got it wrong, it's really just a sign that you haven't done enough practice yet. So over the next year, you got to do lots of these so that these things just come out easily. But if you got the factor of 2 wrong, make sure you can see where that came from. So if you got 222, make sure you can see why that was wrong. And if you just got one of the signs wrong somewhere, make sure you can see why they are the way they are there. E was again a revision question. So we did lots and lots of these in the first term, but if you got a bit rusty, then this was a reminder of how to approach them. Whenever you have anything that has to do with melting points or boiling points, remember you always take the same approach in explaining them, and that's what this is. It didn't use those terms, but if this is a gas at room temperature, it means we're above the boiling point, whereas this is a liquid, which means we're below the boiling point. So that's equivalent to saying that this has a higher boiling point than buta-1,3-diene. And you have to explain that in terms of the energy required to break whatever forces have to be broken when you turn it from a liquid to a gas. So these are simple molecular substances, right? Remember, so it's not about breaking covalent bonds. The covalent bonds will all be there in the gas phase. when you vaporize either of these substances, the covalent bonds don't break. So if you started talking about covalent bonds, or started using the enthalpy change of formation data, which is about making and breaking covalent bonds, all of that's irrelevant, because we're just talking about breaking the intermolecular forces. So the first thing you have to establish is what kind of intermolecular forces do you have? And it's really important you remember that hydrocarbons are essentially non-polar. Because carbon and hydrogen have very similar electronegativity, it doesn't matter that these molecules are not symmetrical. Because the electronegativity differences are so small, all hydrocarbons are effectively non-polar molecules. So that means that we're relying on induced dipole-dipole forces. So the induced dipole-dipole forces in this compound, and the point must be, if there's a higher melting point, they require more energy to break than those in buta-1,3-diene. So it has a higher melting point and boiling point. A boiling point is the relevant one here. So it has a higher boiling point than buta-1,3-diene. But then you've got to say, okay, that's what we've inferred, because we know we're talking about induced dipole-dipole forces because we know these are non-polar molecules, and we know they must require more energy to break because that's what the evidence that this is a liquid, this is a gas is. But the question is why? So you say this is because this compound has a bigger surface area for contact. Remember that phrase. And you can see that just by looking at it. It's just a bigger molecule altogether. Obviously it's twice the size because we know it's an addition product. So it has a bigger surface area for contact with other molecules. So more induced dipole-dipole forces have to break when it boils. Okay, so it's the kind of question that was becoming routine in the first term. But obviously time passes, you learn other things, and the danger is you forget how to do these things. So that was just a reminder that simple molecular substances, you look at the intermolecular forces, you think about what kind they are, you compare their relative strength, you relate that to the energy needed to break them, and hence melting point or boiling point or volatility, whatever it is.